We're in it.
We're rolling?
We're rolling. Say hello.
Oh my gosh. Real analysis. Hi. Welcome to Real Analysis Wednesday.
Wednesday.
Wow.
Real
What
Analysis
episode is
Wednesday. This is episode 5.
Wow, 5 Wednesdays? That's so much time.
This is the primer material for
That's a lot
chapter
of
2
Wednesdays.
on cardinality.
It'd be crazy if it was more than 5 Wednesdays and this wasn't like a weekly thing.
Yeah. All right, cardinality. What is it? Why do we care? What's the point?
Please don't ask me that. I hope you answer that.
I will answer that. We care because it's awesome and
Naga,
cool.
answer the question for us. You're the smart guy. We pay you food.
The cardinality is a set is the number of things in the set.
He can read! That is correct. Cardinality of a set is the number of things in the set. So what we do is we use these little curly brackets to write sets, and then when we put these vertical lines around them, that means the cardinality of. To give you an example, this set, surrounded by the curly brackets, has a 1. We use commas to separate elements. So it has a 1, a 2, and a 3 in it. So how many things is that?
That's 3.
That's, wow. You could be an analytician.
That's 3.
All right.
This
So-
is advanced enough. All right.
This set, what about this set? This set has 45, pi, E, brown, and Texas.
What is that, like 5 things? What's up with that?
You know what? That is 5 things.
Okay, because there's a comma in between each of them. I get it.
This is a thing, that's a thing, it's a thing, that's a thing, that's a thing.
Yep.
The next one, 3.
Okay.
Oh my god.
Why do you
Can
say
not
that,
jump
Peace?
on?
Why do you say it's 3?
Oh, because there's a 3. 10 times 500 is still one thing. And then at -5, 7 squiggly line at the end, it's another one that's separate.
Oh, you guys,
Can you let the viewers catch a break?
you
Oh my
guys could
gosh.
be analyticians, I swear.
See that, Naga?
This is
I'm
like-
on your level.
If you got the hang of this,
Incredible.
you could do anything.
Basic edition. You can do anything.
You could do literally anything in math if you just have this kind of dedication to the
It's not
craft.
even like a basic edition. It's fundamental. Like.
Okay.
This gets old
I make
fast.
knowledge.
For,
Okay.
This gets old really fast for finite sets. For a finite set, you just do exactly what we did here. How many things are there in here? 1, 2, 3 things. How many? 1, 2, 3, 4, 5 things. It's not that exciting when the set is finite. This is why we get into infinity.
Does that mean?
The cardinality of n, this is the natural numbers, stuff like 0 is not natural, fight me on that one. Stuff like 1, 2, 3, 4, etc. All the counting numbers, numbers you would use to count stuff. This blackboard Z right here, this is the set of integers. So stuff like 0, 1, -11, 55, -2, stuff like that. Whole numbers
Okay.
and their negatives and 0.
Yeah.
Okay.
All chill.
Real
All game.
numbers.
What? Real.
This is okay. The way this set is actually constructed is a little bit more complicated than either of those two,
Yeah.
but it is the number line.
All
You got
of the
0
numbers.
here. All of the numbers. Well, all of the numbers on this line. So you got stuff like a half.
Ooh.
You got stuff like the negative square root of 95. You got stuff like pi.
999,000.
Stuff like pi. Yeah, 999,000. That's in there too. That's like over here somewhere.
Yeah, it's that close to pi.
Yeah, it's over there.
This is an exponential graph. It starts off at a half, and then
All that stuff is on there. Okay.
Okay.
Then we have C. These are the complex numbers.
okay.
So this is all numbers that look like this: a plus bi, where I squared is -1, and these two
Hold on, baby.
are real. This is called real analysis, so we don't actually need the complex numbers. So I'm going to move on.
Wait. It's the book.
This notation, however, we just say the cardinality of the naturals is infinity. We say the cardinality of the reals is infinity. This is technically true, but it is misleading because infinity is not a number, and you can't use it as a yardstick of measuring how big or small
But I
something
thought
is.
infinity was a number. Though.
Infinity is not a real number. It is.
What if I put infinity plus
Representation
one?
of a
Infinity,
concept.
that is undefined. Infinity is the concept that there is no biggest number.
What? But I thought, wait, hold on. Ready, gather? I'm gonna break Rob's mind.
Okay.
I thought infinity
don't
was
think
to
you're going to.
represent like a numbers.
Okay.
No.
Okay, peace.
Infinity is the concept, again, that there is no biggest number.
Or smallest.
It's not a number or smallest number.
Okay, so if that's the case, if infinity is like the biggest, right?
It's not the biggest. There is no biggest.
Oh,
There is no biggest number. Infinity is not a number.
Infinity is like basically like the biggest, right?
No, it's
Like,
not.
It's huge.
It's not just huge.
Never mind.
It's not. You're thinking finite here.
Okay.
There is.
I was about to say if it's infinite and big, why doesn't it fight me then?
Do you want to play a
You
game?
really gotta stop.
We can play a game where you name a number and then I name a bigger one, and I will always win because there isn't a biggest one.
Okay. Go ahead.
Okay.
Carry on with us.
We write
We're
this.
playing it?
Infinity's not a real number, but we write this anyway because mathematicians love to abuse notation and confuse the layperson. We need a way to distinguish different sizes of infinities, however, because there are different sizes of infinity.
They both visited.
Okay.
They are not all the same size.
No, that's interesting. So does that mean that one could be bigger than the other? Is that what
Yes.
you're implying? How,
There are, in
like-
fact, infinitely many different sizes of infinity, and the number of infinities there are is bigger than any infinity, but we will get to that. I'm going to
That's
mute
very
Peace because he's hot miking.
That's so sad.
So in order to distinguish
my
between different sizes of infinity, we're going to get some help from something called the bijection principle, which states two sets have the same cardinality if and only if there exists a bijection between the two sets. In other words, let's do
It's a bijection.
Let's do green here. There is a way to pair them up. A bijection is like this.
Yeah.
Oh, look at that. My notes.
What is a bijection?
I'm the greatest. A bijection is a function. You know what a function is?
Vaguely, yeah.
So a function is like a map. You look at the map and you go, where am I? Where am I going? The function that you have as your map tells you where to go. Let's just, we're down here. If my function is f of x equals x plus 1, and I am x, and I want to follow the directions on my map, I go to x plus 1.
Okay.
A function
I get you.
is a mapping such that if you are 1 point, okay, so let's say I'm 5.
Oh, you're really
I'm the
good
number.
at
I'm the
math.
number 5.
Or-
Under
Five.
under the constraints of a mapping being a function, the same function will only ever send 5 to one output. So if I'm 5 and I go through a function, I will land on 10, say.
Okay.
And if I put in 5 again, I land on 10 again. If I put on 5 again, I land on 10 again. Every input has exactly one output.
Okay.
A function can have a few properties. The two that we care about to say whether something is a bijection or not is if it is one-to-one and onto. These are properties of functions. Some functions have these properties, others do not. Some have one and not the other, some have both, some have neither. So consider a function f. Just a function. Say f is a function. And it takes the elements of a, and for every element of a, it gives it a direction. And say, you walk over here in B. F is one-to-one if for every 2 things in A, if two outputs are the same, then it must have come from the same input. In other words, no element of B is hit more than once. So what that means is, look at every element of B here, and look at A, and this is our function between them. This point gets sent to over here, this one gets sent to over here, this one to over here, and this one to over here.
You know what this reminds me of? This reminds me of those tests where you have like on the left is like your like question, and on the right is the answer, and you gotta like put it to each one. But you know that only one is gonna have like one of the answers.
Kinda.
Right?
Yeah. Right.
Yeah. But
so the function
on the other side,
the function
is the opposite.
So the function you're trying to employ is match this to the correct answer.
Yeah.
Okay. This on the left, this here is 1-to-1, because if I look at all the outputs that's in the space, we typically, I might call this the output space, just means the set of things that the function goes to. This I might call the input space. Everything in the output space is hit no more than one time by elements of the input space.
And it can be 0 times it is hit.
Yeah. Is this hit more than once? No.
No.
It is hit 0 times.
Less than once.
However, this on the right, this one is not 1-to-1. Can you tell me why?
Mm-hmm. Why it's not the same as the one on the left?
Not why it's not the same, but why it's not, it doesn't have this property.
Well, I'm guessing that multiple inputs are going to the same output spot.
Yeah, look right here. 2 inputs?
Yeah. Going into that.
Only one output.
Yeah.
So this gets hit more than once. So this function is not 1-to-1. Now, note again that we still have 2 that are hit 0 times. That doesn't matter. As long as there is at least one element that gets hit more than once, this function is not 1-to-1.
Okay. I get this.
Okay.
Now, why were we learning that? Jeez. Freaking.
Now,
bring me back.
the other property is onto. We have to get through onto.
Okay.
This is actually, I think, easier than 1-to-1.
Really? Okay.
A function from an input space to an output space is called onto if for every element of the output space, there is something in the input space that gets sent to that output. In other words, everything in the output space gets hit at least once.
So that's what I was talking about earlier when I was like, oh, but some of these don't, they can be 0.
Yeah.
Or whatever the hell.
So if we look at this
one,
this output gets hit. This output gets hit. This output gets hit. There's only 3 outputs. All of them get hit. So this is onto. Why is this one not onto?
Because the bottom output on B doesn't get hit?
Correct.
Dude, I'm a genius.
Is this function 1-to-1?
Sign me up. No, right?
Why not?
That 1-to-1 is like there is only one output, or one input goes to one output, right? That's 1-to-1. And if there's more than one, then it's not 1-to-1, right?
Okay, so which
this is many to one.
which element of the input or output space is your counterexample?
Is my counterexample?
Yeah. So I make a claim. The claim is false. You say that's false. I say, tell me how you know. You can either prove that it can't be true just because of the universe, or you can find me an object that breaks my assertion.
Okay.
In this case, I say, why is this not 1-to-1? You give me the counterexample of this point. There are many things that hit this point.
Yeah.
That's the counterexample to my claim. What about this one? Is this one 1-to-1?
This one is also not 1-to-1.
How come?
Because of the second point on B is being hit twice.
Amazing. Phenomenal. You now know everything you need to know to understand the bijection principle.
Oh, wow. Okay. teach me a story about the
If
bijection
a function
principle.
has both
Yeah.
of the properties, 1-to-1 and onto,
Oh my gosh.
then it is called a
It's
bijection.
perfect. It's bijective.
So everything gets hit at least once and at most once, and that means everything gets hit exactly once.
Okay.
Look at this.
Sick.
One input, one output, one input, one output, one input,
beautiful.
one output. And everything is hit. Nothing is hit more than once. This is bijective.
Yep.
This function is onto, because everything is hit, but it is not, mnemonic is another word for 1-to-1.
Okay.
It's shorter. That's why I wrote it. This function is not 1-to-1 because of this. Both of these points go to that one.
Mhm.
This function is 1-to-1. It is not onto because nothing hits this.
Okay.
So if there exists a bijection between two sets, then we know that they have the same cardinality. And if two sets have the same cardinality, then there is a bijection between them.
Okay.
How do we know that second part?
How do we know the second part?
Yeah.
In other words, why is this two ways and not just one way?
Yeah.
That is just the definition of cardinality of two things
Because
having the
it's the
same
law,
cardinality. This is how it's defined. Unironically, that is the law. So when we talk about size and cardinality, we can't just say two sets have the same cardinality if their cardinality is the same real number, or it would be a natural number. In fact, we can't say that because some sets have cardinalities that are not natural numbers. So we use this other way. We say two sets have the same cardinality if we can find a bijection between them, if and only if, in fact.
So that makes sense. So you can, if there is a bijection that proves that they have the same cardinality, but how does having the same cardinality prove that it's a bijection?
Editing Rob from the future here. This is in fact this way because this is the way it is defined in axiomatic set theory. It is the definition of equinumerosity that there's a bijection between them, and we extend that definition to infinity to fit our purposes. Like this is the tool that we use. We oftentimes
and then
want this. We want this, so we work at this.
That makes sense. I agree.
So we have done this all to define cardinality. We have gotten to the point that we can define cardinality now. Hell yeah.
Well, we know what cardinality is. In fact, it's the number of things in a set.
Yeah. But we can find it.
How much set we can. You can and maybe should. This is a note. Think of finding a bijection between two things as pairing them up. If I want to try to find a bijection between A and B here, 1, I can pair up with A. 2, I can pair up with C maybe. Ooh, getting fancy. And 3, I can pair up with B.
Is that faster? Is why you're saying like you maybe should?
I think it makes more intuitive sense to think of it that way. Oh, I should probably unmute Peace. Are you no longer hot miking, sir?
I'm no longer hot miking. I was like for 5 seconds saying Rob. I'm trying to remember that. No, slow down. Bottom bit. Okay, let me scroll up just to see the bijection. So they all have to hit, but they cannot get hit more than once.
Yeah.
And that makes a bijective.
Yep. Bijective
Okay, I got it memorized now.
is the adjective describing the function.
So as long as they hit and they're not hitting the same one and everything's being hit, it makes it a bijection.
Yep.
Can you scroll back up
Yep.
further? Go on. Keep going. Yeah, keep going. Keep going. Okay. That's all. I just wanted to read that again.
I didn't hear that.
That's Clover.
Counting infinity.
Okay. That was
You can't hear the
spoilers.
dog in you.
So, can someone please find me a bijection between A and B here?
13, 20, I don't know, 59 soda, 105 cardboard.
What the hell are you talking about?
1320, he said.
That's a valid bijection.
59 soda.
What do you mean, Gallon? He explained it to us.
105 cardboard.
You can just do that to anyone. It doesn't matter.
Yes, as long as like the order doesn't matter, as long as they're not hitting everything.
You can just put it on anyone.
Well, let's look at it. Let's look at a diagram.
See, Gallon, I do memorize shit just when I feel like it.
Can you draw a soda?
Can I draw a soda?
Could be diet soda. 'Cause I'm diabetic.
No. Okay. You're so close. Okay.
There you go.
Yeah.
Piece suggested 39, 20, 59 soda, 105
Yeah.
cardboard.
Yep.
And
Tell
you
me,
can just- you can
tell me,
just-
gallantry. Is this 1-to-1?
Yeah.
Is this onto?
Yeah.
Yep.
Bada bing, bada boom.
Objection.
Okay, but you can just do that like to anything. It's not like, oh, there are rules. Like we are looking through the like a process
All right.
or like a function to assign the input to the output.
You are actually ahead of me right now.
Okay, I'm sorry.
This
man.
is very typically, when using this for infinity,
Yeah.
we can't write down the pairing.
Yeah. Of
There's
course.
infinitely many things.
That's what I'm
So,
talking about.
so we write down the function that maps between input and output spaces, and we check that function for the desired properties.
Okay.
Okay?
We'll talk about that more later, I'm sure.
Oh, I have an
March
exercise.
Madness.
Relevant in April. This is an exercise in thinking about counting in a way that is quick for humans. A computer will do this in 5 femtoseconds if we just brute force it, right?
Seconds. Uh-huh.
March Madness is a single elimination basketball tournament with 64 teams. How many total games are played during March Madness?
So I'm a little
63.
embarrassed. Okay.
We have an answer from the crowd. Why do you say 63?
Because math.
Jesus Christ.
Because
weird.
half of 64 plus half of that number plus half of that number all the way down to 1 is it totals to 63.
Anaka has described the way a computer would perform this task.
Yeah, that sounds
Which-
about right.
Is fine and dandy if we have computers.
Makes sense.
I love computers. They count fast. Wonderful. No computers. No adding. You can do this without any arithmetic.
Okay. Draw the whole tournament bracket then.
You need, well, not quite. What happens every time a match is played?
Someone gets eliminated and someone wins.
Okay, 2 things. Someone wins and someone gets eliminated.
So there are 63 total eliminations, so there must be 63 games.
Okay. That does follow if we then also say every time 2 happens, a match is played. There are no matches played which do not result in an elimination, and there are no eliminations that are not the result of a match being played. Can we agree on that? Is that true? Objections?
So you're saying there's like no draws and shit? Or what?
There are no draws. In America,
Okay.
are you kidding? From this, we can conclude that the number of matches played is equal to the number of total losses that happen. And it's single elimination, so every time someone is eliminated, they're gone forever. With one team standing at the end, that means that all but one of them have been eliminated. So 63 eliminations. We know that the amount of eliminations is exactly equal to the amount of matches played. So there are 63 matches. Sense make or no?
Yeah.
Questions?
Yeah, that's real.
Peace, you're quiet. Talk to me.
No, what you mean? I'm listening.
What if I have screw March Madness? We're gonna play our
Okay.
own basketball tournament.
Yes.
Single
That's what I've
elimination
been waiting for.
with 1,024 teams.
Okay.
How many matches are played?
1,023.
How come?
Is that still true?
Because
God.
there's still
It is.
1,023 teams that are eliminated.
This does.
Okay.
If we choose a number that's not a power of 2, you can be like, they took a bye. It doesn't count. Editing Rob here. If we choose something that's not a power of 2, this does not change the calculation one single bit. Every team still needs to lose exactly once except for the winner. Counting infinities. I said A and B, and then I used S and T because I'm a dummy.
Nice.
Hold on. Let me write down S and T. Two sets have the same cardinality. If and only if there's a bijection between them. This is the bijection principle. We know this already.
Yeah, 1-to-1 and then go on to.
1-to-1 and on-to function between them. Wonderful. Okay.
Okay.
We then have cardinality of S is less than or equal to the cardinality of T, if and only if there is a 1-to-1 function from S to T. So that means we can hit everything in T at most once and still like be a function. So if we pair these up like this maybe, and like that, this is a 1-to-1 function.
Not onto.
It is not onto. It is not onto.
Still, yeah.
And we have our third cardinality of S is greater than or equal to the cardinality of T if and only if there is an onto function from S to T.
There's not, because there's two.
As in, if they're, well, I'm going to draw a different S and a T for this one. So if I have an S and a T, I give this one a bunch of stuff and this one a little less, everything in T gets hit. So there is a way to hit everything in T. Whether or not we have excess is not relevant for the last claim. My man David Hilbert and his hotel.
Oh no, not.
Everyone loves Hilbert's hotel. It's fantastic.
Oh
We all
no,
love
not
it.
Hilbert's hotel. No.
It's fine. It'll be okay.
Rooms of infinite hallways.
It'll be okay. I
God
promise.
damn it.
Other way around, I guess.
I swear to God, if there are infinite customers.
I swear to God, if there's a customer for every real number, we can't fit them all. Hilbert's Hotel is the biggest hotel in the universe. It has infinitely many rooms, one for each natural number. Okay, so there's a first door, second door, third door. There's a 69th door down here somewhere.
Well, I got this.
There's a Google millionth door down here somewhere, etc. Now here's the question.
Yep.
I'm tired. I'm trying to take a nap. And Hilbert's Hotel is the only hotel around. But alas, the no vacancy sign is lit. Every room is occupied.
Oh shit.
How am I going to fit?
Oh God. Wow.
You're in America, right?
It's pretty likely that.
Wait, no. Hear it out. I want to hear Peace's solution.
Peace, lay it on me.
All right, so since you're in America, you most likely you have a gun on.
Okay, I'm cutting that out. Does anyone else have an idea? I'm really tired, man. I need a room to sleep in.
Well, you can do odds and evens.
What do you mean?
Okay,
What is this guy talking about?
like all the rooms are occupied. Well, if you
Mhm.
divide the customers up into odds and evens, right? It creates another set.
What? Why is that helpful?
Okay, so I've successfully divided the rooms into odd rooms and even rooms. Hooray.
Yep.
How?
They're still all occupied.
Okay.
So
Rob?
yes.
Can you ask every single, like, over the infinite PA system to move down one room? Could you do that?
I think so. Why don't we try that? Okay. So
And then you get room one
here's me.
because you're a special boy. Yeah.
It's me. I knock on this person's door
Fucking weird.
from above, and I say, "Move to the next room." And he goes, "Oh, okay." And he moves here. And this guy knocks on this door, and he says, "Hey, can you move to the next room?" And this guy's like, "Okay." This guy knocks on this door, and he says, "Hey, can you move to the next room?" Now, I am in the hotel.
Yep.
Are
nice.
there any people currently in this hotel who do not have a room to stay in?
Maybe like one briefly that like moves down and is like, oh shit, I gotta get a new room, and then like, I'm gonna say no. I'm gonna say no.
Why not?
I feel like everyone's got a room.
How can everyone have a room? There was no vacancy, and then I showed up.
Okay, that's
I mean,
fair.
I think the statement would just
that's
be
real.
wrong to begin with, because infinity there is no end. So now all rooms cannot be occupied because it goes.
Okay, so maybe then I was right, and then there is just one guy, or not just like one guy, but you know, there's like a guy that knocks on another guy's door, that knocks on another guy's door, and that just goes on for infinity because that's how infinity works.
Yep.
Okay. If you want to claim that there is someone without a room, which one?
No one.
It's one guy very briefly, and then the next guy very briefly.
No, everybody has a room because
No, one guy very briefly he doesn't have a room, and then another guy, and then he takes the next guy's room, but then they don't have a room.
But at the end of it, they will have.
What do you mean the end of it?
At the end of it, everybody will
What
have.
end of it? There's no end of it.
Oh my
Peace.
Okay.
God.
So
It's
rather
infinity.
than saying at the end of it, okay, what we will say is there does not exist a person in this hotel that will go unhoused.
That's real. That is true. Yeah.
Because if I want to be housed, I just go to the next guy. I say, hey, you got to move. You got to scoot. And he scoots.
Mhm.
And now I'm occupied. I have a room.
Yeah. That is real. If we're looking
And
at
that's
it
true
as-
for
as-
every single one of these rooms.
Yes.
There is no room for which that is false. Therefore, all of them are still occupied. Everyone still has a room. But I'm also in there now. What if I show up with my friend Gallantry?
Oh my God.
Oh man, I need a freaking room. Can you draw me a helmet?
That's your ponytail. Me and Gallantry show up. How are we going to fit?
You
one single?
do the move everyone down thing twice.
Surely that would work. Can we share a room? Are we that close? How close are we in this?
You killed my wife, so we cannot share a room.
But he hates Jennifer, so it's okay.
Sorry, Jennifer.
Jennifer, no.
But I do want you to be next to me, though, so that I can haunt you through the wall.
Okay.
Uh,
Are you dead?
What about then?
Okay, well, I think Anaka's solution would be right. I mean, you just do it, and then I do it to you, and I'm like, hey, move over.
So you want me to go into room 1 and say, hey, can you tell the next guy you need his room? And then you want to take my room and I have to do it again?
Yeah.
yeah.
How
I
about,
mean, it will solve the issue.
can I do this in one motion?
Sure, man. I'll allow that. I don't know how you're gonna do that.
Naka, how do we solve that?
Oh, maybe
you
can
can-
we do 2 at a time? Can we be like, hey, 1 and 2, go to 3 and 4?
I have a better idea.
Okay.
You can knock on
You can show up with
infinite
it.
doors.
Okay. Yeah.
Knock on everyone's door. No. You go back to the PA system, and then you tell everyone that's an even number room to go to twice. You tell everyone in every room to go to the room that is equal to twice their current number, and then you now have infinitely more rooms.
Oh yeah. So then he will be at 1, and the other guy will be at 2, odds and evens.
Oh, but then that doesn't work because now you don't get to haunt Gallantry.
I wouldn't be next to Gallantry in room 1 and 2.
Yeah. That
Oh,
would
man.
So you do that. You get infinitely more rooms, and then
Okay,
you
and then you kick
And
the
then-
stool
and then-
out.
and then you switch rooms with whoever's next to Gallantry, and then it's
Okay.
solved.
Why don't I tell the person in room 1 to go to room 3 and knock on his door? I tell the person in room 2 to go to room 4 and knock on his door.
That's what I was
And I tell the person in room
suggesting.
3 to go to room 5 and knock on his door.
Jesus Christ.
Prime?
Let's just
Is that what
shift.
you're getting at?
Let's just go.
Everyone
and,
always goes to the gun first.
let's just go and then
they
shift
don't
them
even
all
think
down by
about it.
2. Then these 2 rooms will be open. I can go in here, and Gallantry can go in here, and I can say, "Oh, you need to release Ultra Ball." And can my infinitely long marching band be accommodated?
Yes.
And Aka says yes because he already gave us.
It depends.
Everyone-
Have they won any state championships?
No.
Okay, then no,
Albert's
we're
Hotel
not
is for
just-
winners. You stay outside. If I have one marching band person for every natural number, I can get on the PA system and I can say, everyone go to the room twice your number. Every single odd room will be vacant, and my infinitely long marching band can shuffle into an odd numbered room. Okay?
Okay. Yeah.
Sense make?
Sense make.
Okay.
That's me.
Oh,
Well talk.
those are the answers. Yes, yes, yes.
Nice.
Incredible. Oh, so we just have to scroll down to find the solution.
Oh, damn it. Why didn't we think of that?
Do these solutions,
nice
and
people.
everyone fits. Okay, formally, the cardinality of all the natural numbers is equal to the cardinality of the natural numbers without 1. Even though the natural numbers without 1 are a proper subset of the natural numbers. And that means there are things in the natural numbers that are not in the natural numbers without 1. For example, we also have that there are as many even numbers as natural numbers. There are as many multiples of 3 as natural numbers also. There are as many powers of 10 billion as there are natural numbers. Some bijections, just to tell you.
Projections.
If we define f of n, or f from the naturals to the naturals without 1, we can simply say shift everyone. This person goes to the next room over. Fantastic. And then we fit everyone. And 2n, this just means the even numbers. We can define a function. You go to the room that's twice your number. And this shows that there are as many even numbers as natural numbers, which should be weird because the even numbers are a proper subset of the natural numbers.
I'm a little lost in the sauce.
Okay. Talk to me about it.
Well, what does bi mean in this?
What do you mean?
That again. Okay, so f is on like the left, right? It's like on the fucking equation, right?
Oh,
and
yeah,
then,
yeah,
like,
okay.
After the bi, it's f again, and then
Yeah,
so is
yeah.
that like equal or something?
So I'll tell you what this notation means.
Yeah.
So this right here means f is the function in consideration,
Okay.
and the input space is the natural numbers. That's what this
Okay.
fancy n is. And the output
Yep.
space is the natural numbers without 1.
Without 1. Okay.
Yeah, just this is a singleton set. Note the curly brackets, and note that it only has the one thing in it. It has 1 in it.
Okay. All right.
This minus sign means set minus, which means this just without 1. That's what it means.
I get that. And then the other part of it after the bi.
By this. So what this means is that if I take something in here, this is the
Yep.
input, its directions to the output space are given by this. So for example, f of 4 is 4 plus 1 is 5.
Curly bracket.
No curly bracket. This is just this is just like an aside. That's what this means.
Okay. So that is what the thing to the immediate left of it means.
Yeah.
With the numbers subbed in for the n.
You could just say this is your function, but to really tell
use
you
the function.
to tell you that this is the input space and this is the output space, we use this with the arrow. Because I could just tell you this, right? If I say this is my function, we don't really know what's a valid input. Can I put I in here? No, we can't, because my input space is the naturals and I is not natural.
So you input the arrow.
Well, we input things that are in here. This arrow is meant to visualize we're taking something from here and we're putting it in here.
Okay.
Okay, and so the same thing applies to down here, G from n to n. Anytime you see like this, letter, colon, set, right arrow, another set, that means this is a function. And we define this function by this rule. So, Gallantry, why don't you tell me what G of 3 is?
Would that be 6?
How'd you get 6?
Is it 2 times n?
Yes.
Hell yeah.
Wonderful.
We're math?
We're doing
Yeah. This is going on YouTube.
This cookie character.
Oh.
Introduce yourself.
We have a new character.
No.
We get to something a bit weird. You could tell because I wrote something a bit weird at the bottom. This is the integers, recall? This is -1, 0, 1, 5, -13. Q, this is the rationals. This is 1/2, 3/4, 1/18, negative 100, stuff like that. Things that can be written as a fraction between integers. This also means 5 and negative 10 and 22 over 7 are in here. Or this is not a closed bracket. This is a ... closed bracket. Do you know what this is? All the rational numbers? There are as many rational numbers as there are integers. How much sense does that make?
That doesn't make any sense.
Why not,
Makes no
Anaka?
sense.
Because you can write every what's the z?
The integers?
You can write every integer as a rational, but you can't write every rational as an integer, so there must be more rationals than integers.
But we know that sometimes, even though one set is a proper subset of another, they can have the same cardinality. So that's actually not good enough.
Damn. Said you're wrong. Garen, what you got?
What do I have?
Yeah.
Okay, well, I'm a little confused by maybe the examples.
Oh, well, you can also write there's between any given rational or real number, is that what they are? Z
is the integers.
Between every integer number, there's infinite amounts of rational numbers.
Okay.
I don't know where I'm going with this, because cardinality, you can multiply it by, and it's still 1-to-1 and onto. I don't know. Where are we going with this, Rob?
Well,
I feel like...
First off, you feel like? What do you feel like? Tell me.
I feel like this is a bit weird, because
Also a bit.
there are an infinite amount of things between each integer number.
Mm-hmm.
They're infinite.
There are also infinitely many rational numbers between any two rational numbers. Yeah?
Yeah.
So, like, come on, man. You're kidding me. Well, what's up with this?
Yeah.
Well, even though Q is dense in itself and Z is a proper subset of Q,
Okay.
we can still find a bijection between these two sets. You can write it down explicitly. This has been done, but it takes a lot of ink and a lot of time. So instead, we will draw a nice picture. And
Yes.
the picture will be so convincing that you will believe this claim. Does that sound good to you?
Rob, you sound like you're this may fall on deaf ears, but you sound like you're doing one of those like Jackbox presentations where you just like have to make up the thing you're presenting right now. I have no clue what the fuck you're talking about. But I'm ready to see this like legendary fucking picture.
Okay. I know for a fact that the picture is already drawn, so I'm in fact going to stop streaming for a second and erase it.
Okay.
Something that we proved in chapter 1 was that composition of bijections is a bijection. So what that means is if we have a function from A to B is a bijection, and we have a function from B to C, that's a bijection. Then G composed with F from A to C is also a bijection.
G composed with F?
What this means is that we take something from the input space.
Mm-hmm.
This is we take something from the input space and we do F to it first. And that gives us something in B.
Oh.
Then we do G to the result, and that gives us something in C.
Odd. But okay.
So we compose these two functions. We just do one after the other, and we read it this way.
Yeah.
So F
Of
first
course.
and then G. Just because.
The way that you read things.
You know, the way you read things right to
They
left.
do this in like arithmetic in a very similar notation.
Yeah.
I feel like a transfer student halfway through the year.
So if we compose
You are
two
halfway through the
bijections, the result is a bijection. We know that the cardinality of Z is equal to the cardinality of N. Why? Ponder that if you care. So actually, we just have to show that there's a bijection between the natural numbers and the rational numbers, which seems like it should be harder, but it's not. And I'll tell you why. The challenge really is to list all the elements of the rational numbers in a single file line. We can imagine we have this, and then we just set up down here. We have 1, 2, 3, ... And all we do is we just pair up the first one, pair up the second one, pair up the third one. And it's that easy. So if we just manage to make a comprehensive list of all the rational numbers, the bijection between that list and the natural numbers follows immediately. So all we have to do is make the list.
Okay. The whole list? The entire list?
The list of every rational number.
Seems easy.
How
List every.
am I going to do this? There isn't a next there. If I have a rational number,
Yep.
What's the next one? This is why this is tricky. There isn't a next one.
Oh, okay.
If I claim that any rational number is the next one, I just say the midpoint between them is also rational. That's a counterexample to your claim. There's one that's smaller. This is an issue, but it's solved with a very beautiful picture. I will show it to you. We set up the following grid.
The picture.
Here's the picture.
Oh.
We do this.
I'm ready to be
1,
convinced.
2, 3, 4. This is called Cantor's diagonalization. No, this is not. This is called the winding bijection.
This guy's lying.
5, 6, 7, 8. Boom, boom, boom.
To infinity.
1, 2, 3, 4. Boom, boom, boom. And we do this. 1 over 1. 2 over 1. 3 over 1. 4.
We're halfway.
1/3. Will someone please witness to me that every rational number appears in this grid?
What?
Every
not with this.
rational number appears in this grid.
Do I have any
I can't say I agree.
objections? You disagree because of 0 and the negatives. Is that true?
I'm more disagreeing about that there's an infinitely continuation of this grid that you have not drawn out, unless those are implied.
Should the dots imply that?
Those are the dots. That would be the dots.
Okay.
So
If we're
I'll
implying that, then sure, I'll agree.
Did you not
and
say that
I thought
it's
you had a
hard
really
to-
good. I thought you had a really good objection because of the zeros and the negatives. It's going to turn out not to be an issue. Okay. How do I list everything in the grid? How do I do it?
Do you list everything in the grid?
How do I list everything in the grid?
What?
What do you mean by that? What?
How do I do it? How do
you
I list
list every
everything in the grid
rational
from
number?
left to right in a single file line?
Maybe on like the diagonals. I don't know, man.
Maybe like on the diagonals, he cried. So maybe something like this? That's way too thick.
Yeah, maybe.
So maybe something like, I say the first number I list is
Right now.
1. Then maybe the second number I list is 2 and then a half. Then maybe a third. Crucially, we're going to skip 2 halves because that's the same as 1. 3, 4, 3 halves, 2/3, a fourth, all good. This is the same as a half, so we're actually going to skip it. We're going to skip this one too, and we're going to skip that.
Okay.
Now, if I continue in this manner, which rational numbers am I going to miss with this line?
Have you missed any yet?
No.
Okay.
I actually
0.
This is like the better way of drawing it.
0.
You've missed. You're going to miss 0.
This guy's gonna miss 0.
Okay. I'm gonna miss 0, so I say, oh no. My infinitely long hotel is all occupied. How do I fit 0?
This is terrible.
You shift it down by 1, and
shift it
that's
down by
already
1.
covered.
And I can include 0. Bada bing, bada boom.
And then to get the negative ones, you just double everything and get double the infinite space.
Bada bing, bada boom. It's so easy. So, in fact, we've shown a few things. The cardinality of the natural numbers is equal to the cardinality of the positive rationals, which is equal to the cardinality of the entirety of the rationals. Now just draw a line that picks up all the elements. Perfect. This is what I did earlier that I wanted to erase, but I forgot it was there. This property, if we can find a bijection between a set and the natural numbers, this is an important property. We say that the set in question is, big keyword, countable. The elements are able to be counted in a systematic manner without missing a single one. Wonderful. You can say that the set itself is countable, or that the cardinality of the set is countable. I'm pretty sure. I don't think anyone will get mad at you for that.
The comments can let us know.
The PhD students in the comments.
Get mad at this guy or
Okay. What's the point, Rob? You said some infinities are bigger than others, but we've found that there's nothing bigger than n so far of what we've tried. So, like, did you lie to me about different infinity sizes? Is there only one infinity?
Yes.
Damn it, Rob.
Well, no. Are the real numbers. There are strictly more real numbers than there are natural numbers.
You say that again?
Big highlight right here. There are more real numbers than natural numbers. The cardinality of R is strictly greater than the cardinality of N.
Oh. Because it's including more, like, in-between numbers? Like...
Well, I will show you why. So, George Cantor, back in the day, came up with something called Cantor's diagonalization argument.
Yes.
Which proves that any...
Why am I scared?
The actual thing it proves is that any list of real numbers is incomplete. I'll say that again. What Cantor's diagonalization argument shows is that every list of real numbers is incomplete.
And how do you figure that? Is it like because you're missing the in-betweens, or because you can't list every number in infinity?
I will show you that the unit interval from 0 to 1 is strictly greater. The cardinality of the unit interval is strictly greater than the cardinality of n. If I want to list all the real numbers, I'm going to have a hard time doing that without also listing everything in the unit interval. So if I can show that I can't list everything in the unit interval, then I can't list R. This is Cantor's diagonalization argument. Say, for the sake of contradiction, that I have completed a list of every real number. Say I have the first one, the first digit, the second digit, the third digit, and let's say I have listed every real number thusly.
Mm-hmm. This looks kind of familiar, a little bit.
I'm going to sidetrack you a little bit.
Oh.
And we're going to play a game.
Okay.
I'm going to write down 5 binary sequences.
You're doing this out of our purview.
Yes, you don't get to see them. And I'm going to write down the numbers for the viewers at home. Like and subscribe if you haven't already. Hit the bell just below the screen. Just below the screen, I have written down 5 separate binary sequences that are each 5 digits long. Construct a 5-digit binary sequence that is not one of mine. You get 5 yes or no questions about any of the sequences.
This is tricky.
So the task is now construct a 5-digit sequence that isn't mine. That isn't one of mine. You get 5 yes/no questions.
Okay. I feel like I got it. What if we just ask like, hey, is your thing 11111? Right? You following, Naka? If we do that,
This does also work because we either in those 5 find one that isn't that,
Yes.
or find 5 that
are that,
that, and then we just can
Pick a
produce
different
one that
one.
isn't those 5 exact ones. So that would work.
You'd have to ask, is one of his that?
Yeah.
So yeah, go ahead, go with that.
All right, Rob. Is one of yours 11111?
You must ask me a question about a particular sequence. You cannot ask me about all of my sequences.
Oh shit. Is the first one? No. Okay. Well, that changes things then.
If you do this correctly, you will have a 100% win rate.
Okay. So that's the goal, not just like get pretty damn close, which we probably could.
You could just generate a random one, and there's like a 27 in 32 chance that it's not one of mine.
Yeah.
But be sure.
Okay, let's be sure.
Like there's a gun to your head and also the hard drive containing Ultraballin.
Wow.
I feel like that's more important to you than me. But I'll do it for you.
Can you ask 5 yes or no questions about any particular sequence?
Oh, wait. Oh, no, that doesn't work. Never mind. Oh, fuck. I really thought I had that. Damn. Oh, wait, maybe it does. Maybe it does work. Can we just ask if every sequence is 11111? We could just ask, like, hey, is this sequence 11111? Is this sequence 11111? And then assume...
That only gives, because if we hit a yes in there, then that's not a valid answer, and that ruins our 100% win rate.
Okay. Damn. Yeah, that's real.
Your odds by 1.
True. Just better than none. I thought I had it. It would work if that specific one is wrong. Maybe.
Do I put a think timer on this in the video?
No, let us cook
Okay.
and cut it, and you can edit the video.
Okay. I'll let you cook.
I want to cook this.
I feel like Peace has an idea.
Can I go to the nurse again?
Here's a yes or no question. Do you know where your kids are?
Yes.
Trick question. No, you don't.
No, I don't. No. So I don't have any. Damn, can't say not yet.
By the way, the think timer meant I put a timer on the screen in the video showing how long the think has been.
Oh, sure. Go for it.
I've done that on myself a few times.
Okay.
I'll have Subway Surfers on the side.
Keep them entertained.
Yeah. Or I'll have Ultra Kill gameplay.
I can give you some Death Must Die gameplay.
Oh, I have an idea.
Yeah.
Okay, Rob.
Okay. Yes. Hello.
Okay.
Oh, I just put it. Oh my god, I have to go get them back.
Okay. Let me open a notepad and then I'll start asking questions.
Okay. God fucking damn it.
Hey, it went black. What the fuck? Okay.
I'm ready to hear
You're
it.
taking too long. My laptop's falling asleep.
Okay. Okay. You ready?
Yeah, I'm ready.
Is sequence 1
Okay.
number 1?
Okay.
Is that a 1?
Is sequence 1 first digit a 1? It is.
Okay. Sequence 2 digit 2, is it a 1?
Is sequence 2 digit 2 a 1? Yes.
I don't think this.
Sequence 3 digit 3, is it a 1?
No.
Sequence 4 digit 4, is it a 1?
No.
What does this do?
Wait, Rob, I didn't hear the answer to that question.
No.
Sequence 4 digit 4 is not a 1.
Not a 1. Okay. Sequence 5 digit 5, is it a 1?
Yes.
Oh, I see what you
So,
just did.
a valid-
I see what you just did.
Valid
my
answer
God.
is 00110.
Oh shit! Because it's. Yeah. Yeah. Good
So
job,
I know
Anaga.
that the respective digit is complementary to any of the previous ones.
I was
That makes
thinking
sense.
like that exact thing, but I was like, no, that doesn't make any sense. But you figured a way to make it work. That's
Okay.
smart
Great.
and real.
Now-
good job.
You now know how to construct a number that's not in this list. How do I do it?
I found a complement of. I took a digit that is complementary to a digit in each of the series. Okay. So what are we going to call each one of these numbers? We call them what'd you call them? Okay. Well, I took. So I took the complement of the diagonal, I guess.
Okay.
Which will, because you're complementing at least one digit in each existing number, that cannot be equal to the entire generated number cannot be equal to said existing number.
This is a very heavy abuse of notation, but this just means something that is not D11, something that is not D22, etc. This number is not in the list. It can't be the first number because the first digit is different. It can't be the sixth number because the sixth digit is different. It can't be the 1,000,000th number because the 1,000,000th digit is different. So it's none of the numbers. Therefore, contradiction. Therefore, every list of R is incomplete. R bigger than N.
Yeah, we're still on this math lesson.
It looks like I have something weird. What is it?
What's the doctor have it checked out?
The set of reals has a strictly greater cardinality than the set of naturals. This we have just established. Is there some set S whose cardinality is strictly between them? I don't mind if this takes you a while, because this statement is undecidable.
Okay. Thanks.
I'll
Thanks
save
for
you.
not letting us struggle for the next 20 years trying to prove or not
I'll,
prove.
I'll save you for a little bit of computing power for that one. This statement is unprovable not for lack of trying, but because it is neither consistent nor inconsistent with our axioms currently. And that means we can add it as an axiom or its negation as an axiom and still have some valid math. For any set A, the cardinality of A is strictly less than the cardinality of the power set of A.
You need to find me what a power set is.
I guess, does A have to be
Like
non-empty?
some anime shit.
Hold on. A might have to be non-empty. The power set of A is the set of all subsets of A. So maybe we need a refresher. So the power set of A is every possible way to make a subset out of the things in A. Wonderful.
Okay.
This is the fact that we have.
I agree.
This leads us to a cooler fact.
Oh shit.
There are infinitely many infinities. Because the cardinality of n is strictly less than the cardinality of the power set of n, strictly less than the cardinality of the power set of the power set of n, and so on. The amount of distinct sizes of infinity is bigger than any infinity.
How do you find that?
Well, the proof is a bit long, but it is in the book. It's there.
Okay.
And maybe I'll do a separate video laying that out. This is already getting long.
It's probably a little bit too much.
Been at this for a what?
That's what I'm saying, man.
That's it. Is that the end
Okay.
of the slide?
Wow.
Yeah. All right. So cardinality. We just went through a lot. That
Yeah.
that was an emotional experience that we just went through.
Do you think you could sum up cardinality in a couple sentences from all we've just learned? It's from
Cardinality is here. I'll sum it up.
yeah.
In summation, 1.
Sure.
Cardinality is how many things? How many things in set? 2. Same cardinality, if and only if this backwards capital E means there exists bijection. Really, that's it.
Okay.
We could do like 2.1 here. Cardinality as n countable. Actually, this is if and only if, because that's the definition of countable. Wasn't that awesome?
That was pretty cool. That was pretty
Questions? I'll open to the
cool.
floor.
Yeah. If no one else wants to go, I guess. Do you, like how it like this is obviously very closely tied to infinity, right?
Mm-hmm.
How is it like? How is this commonly used when calculating stuff about infinity? Was the what's it called? Was the hotel that we did like a cardinality thing where everything needs to have one thing that matches up with it? Was that a good cardinality?
Is your question
why you put that?
Is the number of things in Hilbert's hotel countable?
Yes.
So why this happened, perhaps, is your question, is twofold. This is an important thing that we actually do to two numbers when finding a bijection. There's a tricky exercise. My pen no worky.
Yeah, I don't know.
My pen no worky. This is very useful. Hilbert's hotel is very useful if I want to find a bijection between the closed interval 0 to 1 and the open interval 0 to 1. Are you familiar with this notation? You know what this means?
No.
So the closed interval from 0 to 1 means, if I draw a number line here, this means everything in here, including the endpoints 0 and 1. This means everything in here, not including the endpoints 0 and 1. And actually, If we try to find a bijection between these two things by like writing it down such that it's like a continuous function, you're gonna fail. The reason why is because actually one of the reasons why is from algebraic topology, okay, we know that the closed interval and the open interval are not homeomorphic. And that means there is no continuous bijection between them. For most bijections between like segments of real line and the whole and like a subinterval or something like that, you can think of it as a continuous function, but this you can't. There are no continuous bijections between these two sets. And so actually, this is a little bit of a spoiler for the exercise that is exactly this problem.
Shit.
Let's get a set. I have a set. Okay. Let's find a bijection between from the closed interval to the open interval by f of x gets sent to itself if it's not in the set. It gets sent to it, and this is also a sequence. This is a n. So I have this sequence. These are called the harmonic numbers. 1, a half, a third, a quarter, a fifth, yada yada. Send it to a n plus 1 if it's in A, and send it to 1. So what this is basically we have to find a way to fit the problem children are the endpoints. We have to figure out a way to somehow fit both of these endpoints into the line. We can't play Hilbert's Hotel with the entire real line, so we pick out a subset of the real line, and we say, hey, everyone in the real line, 0 and 1 are going to come into your rooms. You all need to shift down by 2. And I'm not sure I actually wrote this down correctly. If I did, I'll correct it, but it's not something I'm interested in getting exactly right now. But that's the idea.
Get them in the comments.
Get me in the comments. I'll just farm you for engagement. I'll farm you. You'll have your negative comment. I'll delete that comment, and you'll comment again saying this guy deletes comment. I farmed you twice.
Then re-add the comment.
This is how we find a bijection between these two things. We have to play Hilbert's Hotel with the harmonic series. It doesn't have to be the harmonic series. It could be the reciprocals of squares. It could be the reciprocals of powers of 2. It could be the reciprocals of primes, but that doesn't really matter because it's easy. If there's an easy way to do something, you bet your ass mathematicians are going to be doing it that way. There's got to be a way to avoid doing all that work.
All this guy does is eat food and do math all day. And he's lazy.
Plays all
Alright.
to kill too.
Questions? Any more questions?
I'm full on questions.
All right, this has been going on for a while. I get it. We're tired.
Yeah, I'm gonna go to bed now.
right.
But that was great. If Real Analysis Wednesday #5, I can't wait to make a cameo appearance.